I'm really very happy to be here, being invited. It's a great honor to be in the Laser Colloquium, and I also appreciate really the warm welcome of the group, of your group, Clara, Celia, and then the whole group. It's really a pleasure being here. So thank you very much. So, okay, I'm from Bordeaux. So Bordeaux is where? It's in the southwest of France, in the Nouvelle-Aquitaine region. And it's a very nice city, as you can see. Well, Bordeaux is very well known for this, of course. But we are also doing lasers in Bordeaux. And in fact, we have the big Laser Megajoule laser close to Bordeaux. And we have the CDR lab that was created in the in order to accompany the building of the Megajoule laser. And Celia is also a laser lab facility giving access to titanium sapphire chains and purple chains. So this is actually the building, as you can see. It's a quite it's an image when the building was still quite young. This is the view from above. This part was an extension. This is a real extension which was done especially for the Horizon LEAP project, which is a big project based on the turbine yak. The goal is 1 joule, 1 kilohertz, 1 picosecond. This is the laser group working on. I'm not working on that, of course. So the Celia has about 90 people working there, and they are in 5 groups. The specialty of France is that we have quite a lot of permanent staff, but there are also, of course, PhD students, postdocs, etc. So the gold group is the laser group. They are doing the laser chain. They are giving access to laser facilities, and they do also laser development. There might be interesting to some people to you to get into touch. We have a group. This is an experimental group. The laser group. We have the harmonics group, which is partially theoretical and partially experimental. They are working on attoscience, high harmonic generation. Of course, now with the Nobel Prize, they are very excited, of course. And indeed, our director, Eric Mervel, he was a postdoc with Anne Livier, and the former director, Philippe Balcourt, who is in the World Group now, he was the very first PhD student of Anne Livier, and he was a postdoc of Pierre Agostini, and he had the honor to assist at the celebration of the Nobel Prize in Sweden. So we are very excited, of course, about that at Celia. So there are theoreticians and experimentalists. In the Petrus group as well, there are experimentalists and theoreticians. They are working on particles and transport, ultraviolet radiation, matter in extreme conditions, X-ray generation, X-ray imaging, dense plasmas. And the FCR group, which is a theoreticians group, where's Luc Berger. And they are working on interaction with fusion for confinement and sorry, there's still some residual French. They are doing simulation, laboratory astrophysics, and they are particle acceleration. And the SLAM group, my group, the short pulse lasers, applications and materials group. And what are we doing? We are mainly working on 2 things. The thing that I won't talk about is the laser-assisted refractive eye surgery, but this is something we only do when we have personnel working on it. Sometimes we have some interns, medicine interns in our group, and they use the laser to do micromachining of cornea, porcine cornea. And this, for example, is a mushroom cut of a cornea, and this was a medicine intern student with us. This is a prototype that had been created even during the pandemic for cornea eye surgery. What I will talk about is the ultra-fast laser matter interaction. Here you see some pictures of our lab. There's an orange laser from the local laser group, laser company, and here is one station. On the back side there's another station, and here's a micromachining station. You see everything's on granites for stability. And our group, our identity is in the last years is especially working in the GHz-burst regime, and this is what I will talk about. By the way, we have a collaboration with Amplitude and Alphanov, which is historic, and now we have a common lab which is signed. There was no celebration up to now because the CNRS people were not free to come and sign with the celebration party, but that's why you don't find anything on the webpage of Celia about it, but we have now a common lab with them. Alphanov is a technology transfer center, Amplitude laser company in Bordeaux. And the ophthalmology activities are together with the startup Ilasis, where we the first director of the Celia is now working, by the way, he's one of the co-founders, and with the University Hospital, the ophthalmology service. So let me show you the group who worked on this. So this is the ophthalmologist. Of course, he's not really in the group, he's attached to our group, but he's working at the University Hospital. He's really operating people. He's a specialist for corneal eye surgery. Then my colleague, John Lopez, he's a permanent researcher. He's an engineer, research engineer. And the PhD students who contributed to the GHz work are Pierre Ballage, he's in the 3rd year, Manola Park, who started in April last year, Theo, who was a master intern and now stays for a PhD, and there was Lou Daman as well as for a Master 1 internship, which is quite short, only 2 months, but she contributed to that. By the way, I have 3 PhD students under my supervision at the ISL who are working with the group on the development of 2 micron lasers with Andolon, but I will not talk about this either. So, motivation for micromachining. I guess many of you know these holes, and you know that with ultra-short pulses you can do very precise micromachining. You can machine almost any material that you want. You can even do intra-volume modifications when the material is transparent. And you have very low collateral damage, as this very famous hole group illustrates. One of the key issues, however, is that it is quite slow. So many people are working on how to increase the productivity. There are 2 approaches. One approach is you can increase the average power, of course, more power. Of course, there are some technological challenges, as the group of Clara can confirm, when you go to high average power lasers. And then when you want to machine your material, of course, you have to, how to use your power. You need special management to that. For example, with polygon scanners or with multi-splitting elements like DOS or SLMs. The other point is, if you can increase the ablation rate for ablation, that's interesting too. And there's the burst strategy. That means you don't take single pulses per femtosecond, but you leave the femtosecond character of these pulses and you put them into a burst. And then you repeat the burst. So when I talk about the pulse duration, I'm talking about the individual pulse here. When I'm talking about the repetition rate, I mean the burst repetition rate, that is when the packet is repeated. And when I talk about the pulses per burst, or PPD, I will talk about how many pulses are within one burst. Okay, and this is of course the intra-pulse repetition rate. First came up the idea of GHz-burst with a low number of pulses. Even with increasing in other, these mechanisms is still under study, and GHz-burst machining is one of the subjects. There are many things to explore. So this leads me to the outline of my talk. I will give some introduction to GHz-burst micromachining and tell you what happens when you do that. I will briefly talk about the laser systems, because there are actually the PhD student who worked on it, he made 3 systems. I will show you 2 very briefly, because this work was done at Amplitude at the company, not in my lab. And I will show you some ablation studies to prove how all these that I will explain in the introduction we found out. This is the way how we found out that. And then I will talk about dielectrics, because ablation studies we did mostly on metals and on semiconductors. And I will talk about dielectrics. Well, percussion drilling is some ablation too, but you always ablate at the same point. Then you get to percussion drilling with dielectrics, and also cutting of dielectrics in the burst mode. And I will always conclude on these different parts. So let's start with the introduction to the GHz-burst machining for the non-expert, that everybody knows what I'm talking about. So it was first proposed by the group of Ilmar Ilgay, and he had very nice papers in Nature in 2016 and one in Optics Letters in 2018. And he suggested what? To put N pulses, quite a lot, into a burst, the pulses, individual pulses are femtosecond pulses, but you lower the energy of each pulse within the burst. However, we have a certain burst energy there. He observed an increased efficiency of the ablation process, very nicely illustrated here. Very high ablation rates were obtained. This one is copper, and this one is silicon, so on a metal. And on a semiconductor, he could show that the ablation rates here given in micrometer cube, or you can measure it in millimeters cube per minute per watt. There were really outstanding results, and many other groups were inspired as well. Amplitude was inspired with the laser development. We were already working on gigahertz oscillators, and our group was inspired to investigate this regime. So, what was observed? So this is the repetitive single pulse case. Okay? You can measure some ablation rate. That was an old work of John Lopez. Other groups, Lithuania, for example, they used the GHz-burst. They saw an increase for line scribing. And then, in our work with GHz-burst, we could confirm the observations of the Ilma group. We saw an enhancement. And for example, what we saw, this is the case of copper. These craters are in copper. When you increase the number of pulses, you keep the intra-burst repetition rate within the burst. You keep, you just add more pulses more and more. What you can see, you increase the ablation. This is what we say. Later on, some people were working about dielectric, also cavity milling, ablation experiments. For example, the group of Beat Neuenschwander, they observed in sapphire an enhancement of 6 times higher ablation rate in the burst mode. However, that was on the detriment of the surface volume. This was confirmed by another group here in these nice optics letters. You see, the ablation rate increases, but there was a detriment on the quality. But sometimes also the opposite was observed. Sometimes people observed, for example, Beat Neuenschwander, he observed on metals not an increase, but a decrease of the efficiency. So how does this go together? He used a standard burst. The answer is in the, what are the laser parameters? What are the burst parameters? Here in this paper, Beat Neuenschwander, he showed surprising tremendous reduction of the specific removal rate. So, why this? He was working in a regime, repeating the pulses, megahertz to gigahertz, but each individual pulse was operating above the ablation threshold. That means already with the first pulse, you ablate. And then in metals, depending on the rev rate and the material, heat diffusion and the specific ablation rate of this metal, you could even see with the first pulse, you're increasing, and then with the second pulse, you're almost nothing works. There's nothing ablated. Why? Because the first pulse comes throughout the matter, and then the second pulse is shielded by the ablated matter that comes from the opposite direction. And this was this paradoxon of even and odd pulses, and you saw sometimes it's better and sometimes it's less good. It was really odd numbers gave better ablation efficiency than even numbers in this regime. Ömer and we are in a regime where each individual pulse within the burst is below the ablation rate. So that means you need lots of pulses, many more. This was, well, one is not really a burst, but from 2 you can talk about a burst. From single pulse to 50, you see these strange effects. And here, in this regime, this is totally different, because with a single pulse of the burst, you wouldn't ablate at all. And these were the studies that I will show you later on for the ablation efficiency that we saw. So what is happening? What is happening? This is the case of silicon. We have a burst where you still are below the ablation threshold. We form a bump like this which is similar to welding, to a familiar with that. Then, if you are around the ablation efficiency, we could, by accumulating, so we are below the ablation threshold, we can explain it. We are accumulating heat during this phase, where we are still below the ablation threshold. There's some volume affected inside. Of course, we have some, depending on the material, some diffusion length of the heat, which is given by the diffusivity of the material, and of course, the burst duration. So the temporal taking is very important. So we don't ablate, but however, as one pulse comes after another within the burst, the time is very short, so we're accumulating on a certain range some heat. Do we want to avoid heat for femtosecond micromachining? Yes, but if you can accumulate heat in a wanted way, in a way that you can choose how to use it, then it can be beneficial. Because then, so you see, when you're heating up, our group showed when you're heating, the ablation threshold goes down. Well, I would rather say it's when you want to go on a mountain, when you start from sea level, the way is much higher than if you are already on a base camp, which is quite high. It is more this effect. So the ablation threshold is not really lower, but you are very closer to it. So, of course, the difference gets lower. And then, when you reach the ablation threshold, the heated material is ejected. And this is what Oehmer called ablation cooling, because the ablated matter takes away lots of the heat. Of course, there's some residual, but not much heat that is residual. So, ablated matter takes lots of this heat. This is what we call ablation cooling, and the crater depth, that is what we observe, is really in relation with the heat diffusion length. Okay? So, but still, now we are here. Still we are here. There is some layer or some volume of the material that is preheated. There's still something remaining. And then we are closer to the ablation threshold. And then we reach it. By the way, the pulse energy is very close then. So that's where you're most efficient. So that means each individual pulse of the burst that is following then, you just need a little bit, and all these pulses can contribute to ablation. And this is what it makes efficient. So here you can ablate material in a very efficient way in this part of the burst. That means the first pulses of the burst, they don't contribute to ablation, and the following pulses after you've reached the ablation rate, they contribute to ablation. So of course you have to find a trade-off to have a good way of heat accumulation, not too much, to avoid unwanted detrimental effects of heat. And you want, on the other hand, the most efficient way to ablate. So in summary, the difference is when you have repetitive single pulses in the kilohertz or in the megahertz regime, the pulse comes, heats up the material, and the part of the energy that is exceeding the ablation threshold will contribute to ablation and take away. Then the material cools down, but not completely. There's some residual heat that is left. There's a very nice paper, by the way, of Stefan Nolte's group, Franziska Bauer, who did experimental studies on it and simulated that already at 200 kilohertz we have some residual heat. And then the next pulse comes, and the next thing, and so on. You have just some residual heat that is saturating at a certain level, but lots of the energy is not used. So what happens in the GHz-burst regime? In the GHz-burst regime, you have time on the nanosecond scale between the pulses within the burst. That means that the time is quite short. The heat is not really diffusing all that time, yeah? Depending on the material, of course. So you have these three stages that I showed you with these three corresponding things. So the crater, the bump is formed due to heat accumulation, and then there's some, due to the heat, there's some stress in the material and forming the bump. Really like when you heat up for welding. This is how it is understood up to now. I have to admit that the GHz-burst regime is not fully understood. Now there's no theoretical model up to date describing really what is happening. So, how do we do our temporal beam shaping? Because it's temporal beam shaping forming burst. How do we do that? And that leads me to show you the laser system from amplitude. So, in this first version, there is a gigahertz oscillator working at 0.88 gigahertz. That means there's 1.14 nanoseconds between each pulse. It's a pulse train. It's an oscillator. It's a ytterbium-based material, so it's lasing at 1030 nanometers, around 1 micron. Very stable cavity, small cavity, at this repetition rate, of course. Then you have a amplifier stage for the pulse energy management. Okay, you have to form the pulses, and you have to amplify in 2 stages. And then there's the laser head with the last booster amplifier, giving an average power of 100 watts, which is based on the commercial Tango system of amplitude. And the output in this first experiment was 520 femtoseconds. Yes, that is a corresponding growth, very nice spectrum. And you can work at 2 microjoule up at 50 kilohertz at the interburst repetition rate of 0.88, then a factor of 2, and another factor of 2, thanks to these optional delay lines. So we have access to 0.88 gigahertz, 1.76, and 3.52 gigahertz. In the second system, the oscillator was changed. I just put an orange box here, because it's from amplitude as well. There's now a 40 megahertz oscillator. So the pulses are separated at 5 nanoseconds, much more. And the optional delay lines allow for generation at 1.2 gigahertz. And then once again, a CPA system, a pulse peaking preamplifier amplifier, giving quite similar results. We are still around 500 femtoseconds. And let's have a look at this pulse peaking system. There's an arbitrary wave generator, which allows for pre-forming the burst train in order to get flat bursts, and the real bursts are quite flat. What does it mean? Because a natural burst would have this form due to gain depletion, because at the beginning you amplify much more and then you have less due to gain depletion. So this is the natural burst, and the first experiments were done with the natural shape, gain depleted burst. And then this is why I showed you the 2 laser systems, and then later on we were working on formed bursts. We were mainly forming on a flat burst, but we made also some studies with a decreasing burst. So these are the ideal bursts, and these are the real life screenshots from your oscilloscope, what it gives, a decreasing burst or an increasing burst. So this is this arbitrary wave generator that allows for it. There was an AOM to pulse peak the wished length of pulses, of course, and there was an EOM as well, just to have steeper flanks, because the AOM is longer time in range. Okay, this is for the laser system. Now, the ablation studies that help us to deduct what is happening that I showed you in the introduction. So the laser system is this gigahertz Tangor. The setup is we go into a machining station. Here is a galvo scanner and the f-theta lens, and then we put the sample here. Everything is, of course, on a granite gantry for stabilization. The study that we did is with craters, lines with a certain overlap. We also studied the overlap. The influence was not that much. And cavity milling with an overlap of 48% in both directions. Direction where you move, and then also what we call the hatch. If we compare these 3 machining strategies, craters, here craters with rounds, craters are round, lines with so In cavity milling, what can you see? Of course, I help you to understand with the colors, because we put the matches that give the same burst duration in the same color. Because you can do, for example, 57 nanoseconds, you can do it at 0.88 gigahertz with 50 pulses per burst. Or you can do it, well, you double the frequency, but then you have to double the pulses as well. If you keep the fluence constant in these pairs, you will what can you see? The curves are the same. Yeah, there's no difference as long as, of course, the individual pulse energy is not too low. I guess there will be some limits. If you even increase the rep rate and then the pulse energy is almost diminished by a factor of 2, well, at a point it will stop. But here you can see that gives the same thing. So it's really the burst duration, which is the key parameter, that will decide what will be the result. And you see, you always have an optimum of the specific ablation rate. So the optimum is related to the burst duration. Same duration gives same efficiency, and it increases because this is 57 nanoseconds, this is 228 nanoseconds, and the red one is 912 nanoseconds. So it's increasing with the burst duration. So what is happening when you look on lines? What you can see here is, once again, the specific ablation rate. You see the same trend. I kept the colors. The quality factor. The quality factor is defined as 1 minus the really positive matter in ratio to the ablated matter. So this is what is ablated. This is green. That's what we want. And what we don't want, put in red, the really positive matter. And you can see the quality increases with the burst duration. So you have the best quality for long bursts. So here you see the really positive matter doesn't really increase, but you get much deeper lines. This is what you can see here. So here you have really both quality and efficiency that are optimized for the same parameter, luckily. What about cavity milling? Cavity milling, well, as you can see here, there's quite a strong rise of the roughness with the burst fluence. So when you increase the burst fluence, unfortunately, the surface roughness increases as well. So here the highest efficiencies come with the lowest qualities. You cannot have everything. So to compare single pulses with burst mode ablation, you can see when you have two short bursts, this is the burst duration. Of course, this is femtosecond, but it's burst duration, the whole version. Then you're not efficient. Okay, you're even lower than for the single pulse mode. And then people, they observe, yeah, it's not efficient, it's not good, but you have to be in the right regime. So when the burst is too short, it's not interesting because, yeah, you're just heating up, but you're not ablating. When you go to longer bursts, then you can profit and you can ablate, and higher ablation rates can be achieved, even exceeding the one of single pulses. And with long enough bursts, even rates with nanoseconds can be reached, and there's, however, better quality than with them. So this is the good point here. To conclude on the ablation, so we saw it can be reduced for line and for cavity milling, but it can be still higher with, than for single pulses. We have a wide range of parameters. The key parameter is the burst duration. And for line scribing, even the good quality comes with the high efficiency. For cavity milling, it's not the case. However, a group at Bosch showed in this very nice paper that you can polish afterwards, and a two-step process with high efficiency ablating and then successive polishing might be a very good solution for cavity milling. That was for ablation. Let's come to percussion drilling of dilate. So this is the experimental setup. Once again, we are injecting in a micromachining station. We have a camera that can observe from above. We have an observing from lateral view. course, this is a good thing. With dielectrics, they are transparent. You can look through with the camera. This is very nice. And everything is, of course, on a granite gantry for stability. So we are just taking a Gaussian beam and focusing it with a microscope objective. And these are the parameters that we will investigate. So what can you, first observation, you have repetitive single pulses and you have GHz-burst. The holes don't look the same. They have a different morphology. In repetitive single pulses, you have a strong conical form, and you have these symbolized here. You have some cracks here at the entrance, but all along the hole, you still have them. With GHz-burst, you have a very, very smooth and almost cylindrical hole. So the morphology is not the same. That was a big study. Let me show you what we saw. Glass drilling. So here are always the parameters. Maybe I will not repeat it every time. You can just read them. And we investigated some different burst fluences. And what do the holes look like? Here for two materials, we have soda lime and fused silica. We have diameters between 25 and 30 micron. And we have depths that are increasing with the number of bursts that were applied. Here, we applied 200, 300, 400, 500, 600, and so on bursts. As we are at 1 kilohertz, that means 200 milliseconds, 300 milliseconds, etc. Here we are at 900 milliseconds, not even 1 second. And you can see there's an increase that looks linear. So we have cylindrical holes in contrast to single pulse drilling. We have smooth inner walls, very smooth in the case of fused silica. We have an almost linear evolution of the depth, and we have a constant diameter. So what happens if we drill for longer times? We drill up to 20 seconds, 19 seconds, and we have for soda lime these curves. And this is increasing fluence. More and more and more fluence. What gives it what will it give in fused silica? It gives the same thing, same trend. You see the same trend. If you look at the scale, the depths are not exactly the same. We have the drilling depth as a function of the number of bursts. You see that's the same here. The same tendency for these two materials. You always have a saturation at each fluence, which gives the final depth of the hole that can be reached. There's no influence of the drilling speed. I will talk about the drilling speed in the following. And the diameter, this you have to trust. I don't show it here. You show it on the first pictures. The hole diameter always stays constant. I already said once here, we don't move the sample nor the laser beam. What about drilling speed? You can get the drilling speed when you look at the slope of this, how the curve is rising. And when you have a closer look at the beginning, you see there are 3 curves that you can fit. There's one very steep in the beginning, middle one, and then the last one, which corresponds to the saturation. So this gives us a mechanism of drilling in 3 stages. First, we have the surface ablation where the plume can freely expand. Then it starts to interact with the side walls. And here you have some other, that's why the slope changes. Here drilling is a bit slower. Here it is faster. And then finally, there's no more energy left. Why? How can the laser beam go down there? Of course, it's internal reflections within the hole. But at each reflection, of course, you have some refraction losses, you have some diffusion losses, scattering losses. And so the energy is diminishing, and when there's not enough energy left to drill, then drilling stops, and drilling is over. So we have surface ablation, deep ablation, and then the separation of the drilling, and there's no energy left. When you have a look on the drilling speed, you can see there is no effect on the fluence of this. You have soda lime here, fused silica here. For surface ablation, almost the same values for all the fluences. So fused silica, within the uncertainty, exactly the same ablation speed. for all the fluences. You have a lower surface ablation speed in fused silica than in soda lime, which is logic because fused silica has a higher ablation threshold. So you need more energy so that it's slower. Seems logic. And you have no effect of the material on the deep ablation speed. So this is really the same values if you're in soda lime or if you're in fused silica. So let's have a look on the burst repetition rate. We kept everything constant, 50 pulses per burst, 1 fluence. And when you have a look on 1 kilohertz or at 20 kilohertz in fused silica here, easy to see, the hole is deeper at 20 kilohertz. So for fixed fluence, at a higher rep rate, you can drill deeper. Now let me show you some comparison between single pulses, megahertz bursts, and gigahertz. So there's quite a lot on this graph. Once more, now you're used to it, you have the drilling depth as a function of the number of bursts. And here, black dots is single pulses, triangles correspond to megahertz bursts, and squares correspond to gigahertz bursts. Okay, you can see many things. You can see, of course, gigahertz burst regime, you have deeper holes. But you can see, we reach them later. And if you have a closer look on this first part, which gives the drilling rate, or the slope is the ablation rate, you have a higher ablation rate in the megahertz burst. But it is somehow logic because you have more energy per pulse in a megahertz burst than in a gigahertz burst. So you drill faster in megahertz burst, but you go further, you go much deeper in the gigahertz burst. So what do the holes look like? Yeah, here, single pulses, no surprise, they are conic, and gigahertz burst regime, they are more cylindrical. The saturation depth is not the same. When you go further, you go deeper. And if you compare megahertz with gigahertz, you have this is for 2 pulses. It's a mini burst, it's 2 pulses, is a double pulse. And this is with 8. And you can see this is more like single pulses, and this has already a trend, especially in the beginning, somehow similar to the gigahertz burst regime. So you have these regimes, and in the megahertz burst regime, short bursts are more like single pulses, and long bursts are more like gigahertz. Not really surprising. So if you have a look on the influence of the burst shape, remember I talked about flat bursts, increasing and decreasing bursts, then you keep, of course, all the parameters are the same, and as the laser system allows to have these different shapes, we don't have to realign anything. It's really comparable. Also, this is the advantage to have this 40 megahertz oscillator between the different regimes before as well. We don't have to realign. It's really the same alignment, so the comparisons are fair somehow, not due to a misalignment in the next experiment. When you have a look at flat burst, increasing burst, and decreasing burst, what can you see? Well, the holes are deeper in the decreasing burst. However, the quality of the hole is the best with the increasing burst. And the flat burst seems to be a good compromise between speed and quality. Really the best quality is the increasing burst. So if you go slowly in the beginning, this is more easy for the material. There's not much heat affected, which is also logic. So if we compare it, here we can have a higher surface ablation, so we go further, faster for decreasing burst, and we have a comparable ablation rates for the flat and increasing. Let's go towards extremely high aspect ratios. How far can we go? Then we have to optimize. First, we take the material, we take fused silica and not soda lime, because when we want to increase the rep rate, you saw we can increase the depth. But soda lime is subject to heat affected zone. The hole collapses. It's even closing here. It's refilling. So we take fused silica, and as you can see, we can go very deep. At 100 kilohertz, we went down, the diameter measured here, so it's between 25 and 30 maybe microns, but we went down to almost 4 millimeters. without moving the sample and without moving the laser beam, the focus. So all along the whole, the walls are very glossy. So it is possible to get aspect ratios up to 150 with this drilling method, with no heat affected zone, at least in the silica. So let me summarize on drilling. You saw the qualities are very, very high. In GHz-burst, you can see a film in real time. It's drilling a hole into silica here. What is still to do as an outlook? Optimize parameters. The process dynamics. How does the material get out? That's really a question. Other materials, other processes, or additional spatial beam shaping, which leads me to the last part, which is shorter, on cutting of dielectric in megahertz and gigahertz burst regime. So cutting has already been shown with megahertz burst. There were 4 pulses within the burst. It's an old work also of the Lopez and Konstantin Mischik, who was a postdoc at that time. And it is a 2-step process when you do it like this. Actually, with the vessel beam, you do a pre-cutting, and then you need some mechanical stress or heat to separate the 2 pieces. And when I talk about surface roughness, surface quality, I mean we look at here, and then there was the RA. I will show you the SA result. Do averaging over a larger surface. I think it is better to give this because you can always find a line where it is very smooth, and better to take a bigger part. Okay, so vessel beam shaping is done with a Mexicon. I don't know if you are familiar with that. We have a first vessel beam, and then we have a reduction system to accumulate the energy in a small volume where we put the sample for this pre-cut. The measured beam, you can measure also the length of the vessel beam by fluorescence or post-mortem, once again in soda lime, as it costs nothing. You can have a look on the length of the modified material. And what we got is 1.2 millimeters length and almost 3 microns in diameter. And what happens when you look above on your sample, on your soda lime sample, oops, sorry, I will fix it now. So what you can see is you have holes, but the holes are, there's something around, some crack around, and you have to orientate these cracks. If the translation movement of the sample is like this, you have to align the cracks in the same direction as you're moving the sample in order to cut. In this way, it will not really work. And we can do it by turning a phase mask. So the results, we wanted to do a fair comparison between megahertz and gigahertz. So we kept all the parameters constant, except that once 4 pulses at 40 megahertz, where we got these results, and 50 pulses within a 1.2 gigahertz burst. And what you can see, well, the results are slightly, the surface roughness is slightly lower, it should be as low as possible to be good, slightly lower than for the megahertz burst. However, you see some sleek part here, so maybe the energy was not enough. I will come to that later. So we have a better cutting quality with the gigahertz burst, and we have the same general trend for both regimes. And what you can see is, if you lower the pitch is the successive pre-cutting, the distance between 2 pre-cutting vessel holes that I showed to you. So when you lower that, the surface roughness is going up again, and not a little bit, quite a lot. What is happening? You form a heat-affected zone, which is symbolized here, and then what is happening is you have a path deviation. When you look from the side view on this sample, this is your vessel beam, and then you will have this. And if you look from above, if this is the trajectory, this is how you move the sample, the trajectory will be this. You can look at with the beam profile, and it is curvilinear, as you can see here, and this is a real sample after treatment. So this is a regime that could be rather, usually you have to avoid it, because the good thing is you don't need any cleaning, the part falls out itself, because we are in somehow a thermal cutting regime, but the cutting plane follows the heat affected zone and not the bezel trajectory, and usually it's not what you want. So there you have to be careful. So to be really fair, we optimize independently the parameters for megahertz and gigahertz. What came out? Left is soda lime. At the right you have AS32, this is a shot glass. So we optimize, and what you can see is you have GHz-burst, better cutting quality. Okay, yeah, the RA is always below the SA. Here you see at the both values. You need a higher burst energy for gigahertz. And here you need more than here, and here you need more than here. It's logic because you have less energy in your individual pulse, so you have to, it has to be enough to do a pre-cutting zone. And a higher overlap is required, so the pitch is lower in the gigahertz case. That means if you want to go to better quality, you have to do gigahertz. However, it's slower because the pitch is lower. Here, just some overview of the operating windows. On the left, gigahertz, on the right, megahertz. Of course, it's soda lime. As you can guess, the green zone is where you have super cutting parameters, super results. The yellow zone is okay, cutting is working, but it's not optimal. The red zone, you have no pre-cutting, it doesn't work at all, nothing happens on your sample. And the gray part is this thermal cutting regime that I showed you, where you have this heat affected zone. So what can we see? Yeah, you need more energy in the gigahertz part to cut. You are less affected by this heat affected zone regime. So it's much smaller. In the case of megahertz, you have to be careful not to be in this part. So really different operating windows. With lots of studies, we found out that. So let me conclude on this last part of cutting. So we were the first to couple this gigahertz burst shape with a bezel beam, and it works, and it gives good quality. It's slower, we saw. What you see here on the film, this is a soda lime sample, which is moved into this is the bezel beam, and here it's pristine, and here it's here we have this pre-cut zone viewed by camera. You can see that. What is still to do? Of course, optimizing parameters, looking at the influence of the burst shape, and trying other materials. Of course, other materials are quite interesting. And on the whole micromachining also, I'm very interested in what people here are doing with longer wavelengths, because we can also think of doing micromachining of semiconductors. So as you can see, Bordeaux is a very nice city. And the PLI conference will take place in June, exactly in that building that I showed you. By the way, it's now this year, so I have a correction here. So in June, if you're interested in laser processing, it's a conference in French and English, simultaneously simultaneous translation. So you're very welcome to see us in Bordeaux, and you can visit our lab, which is a great pleasure. Thank you very much for your attention.